All right, so we're going to talk about rational functions. So a rational function is a function f that is a quotient of two polynomials. So f of x equals p of x over q of x, where q of x does not equal 0. Okay, so if you remember this, sometimes there's some domain restrictions with regards to rational functions here. We're going to talk about asymptotes, both horizontal and vertical asymptotes, and then actually oblique asymptotes. So here, the first one, it says find the domain and graph this, okay? So the first thing is I want to look to see if there's any values of x that I can't plug in. So that way, are there any values that are going to cause me to have a zero main denominator? Well, yes, so x cannot equal 3. Well, that's nice. That's set notation. We want to put it in interval notation, so we're going to go negative infinity to 3. Remember, I can't equal 3, so I'm going to use a parentheses. Union 3 to infinity. So anytime you're in interval notation, you're actually stating the values that you can have. Okay, set just says, hey, I can't have that. Now, if I want to graph this, okay, I'm going to go 1, 2, 3, 4. Okay, I know I can't be at 3, so I'm going to put that dashed line there at 3. Now, what I'm going to do is I'm going to plug in a couple of values on each side of 3 to kind of get an idea of where this is going. Okay, so I'm going to use a table of values just real quick, just to kind of give you guys a good idea of where this is going. So let's say I'm going to use well, let's go 3.5, 4, 5, 6, just to kind of get an idea. We'll go set up another one here for the ones below. So let's go 2.5, 2, 1, 0. Okay, just to kind of get an idea of where that's going. Okay, so if I plug in 3.5, I get 1 over 3.5 minus 3, which is 1 over 0.5, which is going to give me 2. If I plug in 4, I have 1 over 4 minus 3, which is 1. I plug in 5, I get 1 over 2, which is a half. I plug in 6, I get a third. Okay? So that kind of gives me this side of the graph here. If I plug in 2.5, I get 1 over negative 0.5, which is negative 2. This will give me negative 1. I plug in 1, I get negative 1/2. I plug in 0, I get negative 1/3. Okay, so now I'm going to plot these 3.5, 2, 1. Okay, so this part of the graph is going to come like this. Notice that I never get quite to 0. I get close, but I don't get there. Here I have negative 2, negative 1. A third, so it kind of goes like that. And there's my graph. And we're going to talk a little bit about kind of utilizing asymptotes and stuff when we're graphing. So we want to talk about vertical asymptotes. So vertical asymptotes is if I have a rational function, p of x over q of x, and p of x and q of x have no common factors. So I can't reduce it down. I can't cancel out anything. Then anywhere where q of a equals 0 is an asymptote. It's a vertical asymptote, okay? So here, if I want to find my vertical asymptotes, the first thing I need to do is I need to factor my denominator. Okay, so I'm going to factor this here. So this is going to give me, this is x plus 4, x minus 2. So that's negative 4 and 2 are my areas. So my asymptotes here are going to be x equals negative 4, and 2. There's my asymptotes. I have 2 asymptotes for this function. Okay, vertical asymptotes. All right. Now here, I'm going to go ahead and factor this. Okay. Well, if I have a square, if this is a difference of squares, so now I have x minus 2 over x times x plus the square root of 5, x minus the square root of 5. So now I know I have asymptotes. I have vertical asymptotes at x equals 0, negative square root of 5, and the positive square root of 5, okay? So our vertical asymptotes are always going to be where our denominator equals 0. All right. So there's my vertical asymptotes. Probably notice that this is also my domain restrictions, right? So my domain restrictions and vertical asymptotes really go hand in hand. Horizontal asymptotes. Now this is a lot of writing here. So essentially what we're going to do is we're going to look at the lead term of the numerator and the denominator. If they're the same degree, so if the numerator and the denominator have the same degree, what we're going to do is we're going to look at the lead coefficients. So we're going to put lead term over lead term, reduce it. That's my horizontal asymptote. If the degree of the numerator is less than the degree of the denominator, then it's y equals 0. So that would be like if I had x plus 2 over x squared. X over x squared gives me 1 over x. As x gets out towards infinity, the x is going to go towards 0. If the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. There may be a slant asymptote, though, or an oblique one. We'll talk about that in a second. So here I have g of x equals 2x squared plus 1 over x squared. So the first thing we need to do is we need to find our vertical asymptote. So our vertical asymptote is where this equals 0. Okay? So that's going to be at 0. So our domain uses that vertical asymptote. So this is going to go negative infinity to 0, union 0 to infinity. Okay? Now, our horizontal asymptote is going to be y equals 2x squared over x squared. Those cancel out, leaving me with 2. So now my horizontal asymptote is going to be at 2. My vertical asymptote is at 0. Okay? So there's my two pieces of this. Okay? Now, I need to kind of have an idea of what this graph is going to look like. So a lot of times it's convenient to kind of plug a value on each side and see what you get, okay? Understanding that we're going to be on each side of this asymptote, so I'm either going to curve up, curve down, curve down, curve down, or we're going to alternate, okay? So we're going to test it. So I'm going to plug in negative 1. Negative 1 squared is 1, so this gives me 2 plus 1 is 3. Negative 1 squared is 1, so at negative 1 I'm at 3. So that tells me that I'm going to be like this on the left side. Now I'm going to test 1. So if I plug in 1, 1 squared is 1. So I notice that I don't worry about the signs. I don't have any problem with the signs. So there's going to be my graph of that. Okay, they're going to be mirror images of each other. Okay, so they're either going to be symmetric, either across the asymptote or diagonally. We have oblique or slant asymptote when the numerator is 1, the degree of the numerator is 1 more than the degree of the denominator. Okay? And so to find that oblique or slant asymptote, what I'm going to do is I'm going to use division. And I'm just going to use log division just to kind of refresh our memories on log division. So I'm going to go x minus 2, and I'm going to divide 2x squared minus 3x minus 1. So x times y gives me 2x squared. Well, that's 2x. 2x squared minus 4x. Alright, so this gives me x minus 1. X times y gives me x. That's a 1. So this gives me x minus 2. Subtract, so that's positive 1. There's my remainder. So this is really like this. But this goes towards 0 as x gets really big. So I don't really have to worry about that. So my oblique is y equals 2x plus 1. So if I were to graph this, that's my oblique asymptote. My vertical asymptote then is x equals 2, right? Because I have 2. So if I were to graph this, okay, first I'm going to plot my vertical. Now I'm going to graph my slant asymptote here. So I'm going to go plus 1 up to 1, 2 over 1. Okay, so there's my two pieces here. So now I'm gonna kind of test to see where it's gonna fall. It's gonna fall in here. Which part of these quadrants is it gonna fall? So if I plug in 0, right? So if I plug in 0, I get -1 over -2, which gives me a half. I plug in 1, I get 2 minus, this gives me -4 plus 2 is, so that gives me -2 over -1, which is 2. So I know that it's going to go like this on that side. I'm going to go ahead and plug in 3. So this bottom is going to be 1. The top is 18 minus 9, which is 9. Minus 1 is 8. So now I know it's going to come up and be in that piece there. So we've talked about vertical and horizontal asymptotes. Remember, the vertical asymptotes is where the denominator equals 0. The horizontal is, I'm going to put that lead term over each other. The lead term of the numerator over the lead term of the denominator, and I'm going to simplify.